The title of this presentation is Optimizing Materials with Hamiltonian Design. To begin with a presentation overview, we'll be introducing some applications of Hamiltonian and Hamiltonian type frameworks for modeling thermodynamic and related properties of materials. And a lot of these properties of interest can relate from characteristics of the electronic structure, electron-electron, or nuclear-nuclear interactions, such as we'll be introducing through a Hamiltonian formalism for one reference. And although such perspectives are often framed within more applied points of view, such as we want to look at which compounds within some collection or ensembles of compounds would be the most thermodynamically stable in different types of environments, we can also demonstrate how properties of Hamiltonians introduced in pure mathematics can demonstrate new types of interactions that can be modeled in next generation materials. So to form such connections, we draw upon several classes of models defined in statistical physics, which study thermodynamic properties of finite volume systems as the system size tends to an infinite volume in the weak volume limit. And we particularly focus on one recent reference to discuss constructions of a new family of Hamiltonians and how this very much has connections with the more pure math perspective from people in the statistical physics community, and how we can leverage these perspectives for making progress on pure and applied perspectives at the same time. So the reference that we're going to be talking about is Quantum Algorithm for Alchemical Optimization and Material Design by these authors. And it's a really interesting paper because it provides some types of definitions for many types of objects which are used in statistical mechanics. However, it's drawing a different type of attention towards the construction of the Hamiltonian in several different terms which are coming into play and competing with one another for determining characteristics of the alchemical Hamiltonian, which we'll introduce. So we'll want to demonstrate from this perspective and the objects that they define how one can look to more of a pure math perspective and be able to discuss some results that are applied in pure math and how we can make use of both of these perspectives at the same time. And by and large, this is to say that quantum algorithms rely upon time evolution of qubits on quantum circuits. So this is to say that the reference that we're going to be discussing in terms of the Hamiltonian that's given on the left side has connections with more algorithmic perspectives in quantum computing and in quantum physics also, because it's relating to the nature of information from qubits as their time evolve forward along a circuit throughout other points of the time evolution. And this is relating to a paper that I've read and talked about in a couple of different presentations across the channel, which is titled Variational Quantum Algorithms for Nonlinear Problems from Lubash et al. And I've reproduced one of the quantum circuits that's used in their paper, which they use to demonstrate that they can obtain high fidelity solutions to the Invisib-Burgers and the nonlinear Schrodinger's equations on like 2 or 3 qubits, which gives them a proof of concept experiment that they said or that they feel confident could be applied to other nonlinear problems. But before we get into describing the alchemical Hamiltonian and these types of connections that we've been mentioning between quantum algorithms and statistical physics, we can ask ourselves broadly, why quantum algorithms? So there are many different types of problems that quantum algorithms can be used to model and time evolve forward, even though the problems that we're looking to simulate on a quantum computer aren't necessarily relating to quantum physics. For example, in the APS April 2022 meeting a while ago, I provided some proof of concept simulations and how one can obtain the cost function that's used to obtain a solution for a PDE of interest as given in the framework from Lubash et al., which I've described in several other presentations on my channel, from a more in-depth presentation at the Dartmouth Applied and Computational Math Seminar, as well as describing connections between the variational quantum algorithm as an extension and as a generalization of the variational quantum eigensolver, and also how one can look at making use of solutions that are generated for different PDEs as training set data for neural operators and physics-informed neural networks for solving PDEs, as well as finally looking at different characteristics of biological transport from a PDE perspective. So this is to say that there are many connections with the VQA, quantum chemistry, electronic structure computations, and binding affinities, with the last 3 bullet points are topics that we're going to be emphasizing further. And experimental results from near-term quantum devices in industry point to quantum advantage in a very narrow range of applications. So even though there was a recent quantum supremacy experiment by Google that demonstrated that they could run some type of quantum algorithm that would take like 10,000 years for a classical algorithm to run. This was very much a contrived problem in taking a much advantage of the near-term quantum hardware that they had as possible. So it's very much interesting and still a direction of research in current interest to determine whether any type of other additional applications, such as given by the apparatus with the Sycamore processors and the dilution refrigerators, which Google Quantum AI is fabricating, to determine whether, as demonstrated in the reference that's given on the other hand of the slide, whether there can be any type of effective measurement readout that we can obtain from stabilizing a highly entangled state after time evolution to still be able to demonstrate that there's some type of quantum advantage, let alone the much more lofty goal of obtaining quantum supremacy in some types of experiments in the future. And now we're going to circle back and return to the paper that we had introduced as the first reference at the beginning, with which we had been motivating can be related to quantum chemistry and electronic structure in computing different interactions from nuclear-nuclear to electron-electron interactions. And this is given by the fact that in the paper that we have been mentioning and discussing and framing into perspective with quantum computing, the authors define an alchemical Hamiltonian, which is a Hamiltonian which is given by the two parameters r and alpha, where alpha is some constant and r is the atomic positions of the different atoms in the compound, which is given in terms of hr of alpha plus other terms in the Hamiltonian. And first, I want to isolate all the terms of the Hamiltonian so that we can determine which type of interactions the Hamiltonian for the alchemical interactions that the authors introduced is taking account for, as well as being able to demonstrate some other types of interactions with other models of statistical physics, in the fact that many of these types of models, which are defined in terms of probability and mathematical physics, can very much be described and framed within the same type of or very similar types of interactions that are given by Hamiltonian. So first, we can look at the first term in the alchemical Hamiltonian, which is given by the fact that it's given by some function, which is given by functions of little r and big R. And we have to keep in mind here that the little r means the electronic coordinates of the structure, as well as the big R means the atomic coordinates, as well as two summations, or well as three summations. Actually, there's one summation here and two other potential terms here. And the potential terms that we're looking at are electron-electron interactions and nuclear-nuclear interactions, which, as we had just mentioned, given the fact that we have different coordinates for the electronic and atomic coordinates of interaction, our modes of interaction are given as a function of different coordinates. So even though these potentials appear in the term for the Hamiltonian, which we're using to construct the alchemical Hamiltonian that the authors provide in the reference, it's very much interactions and potential terms that are based amongst different sites of the lattice for interactions that we're looking at. But besides these two potential terms in the KE of our term, we also have a summation over other terms which are relating to different potential terms which can relate to various characteristics of the electronic structure that we will want to look at. And the summation are given over different indices which are characterizing different properties of the structure, whether it be the total number of atoms in the compound, as well as other types of characteristics relating to the electron-electron and nuclear-nuclear interactions. So this is very much demonstrating how different terms from quantum chemistry come into play by isolating different interactions which we expect to occur within a compound of interest, and within potential binding events or binding affinities that we can associate to the strength of different compounds or ligands and receptors with each other. This is also to demonstrate that there can be many types of connections between modeling how the thermodynamics of different compounds change with respect to time, or the duration over which an experiment is in an assay or other experimental procedures carried out. But the remaining term in the alchemical Hamiltonian also has two other terms which are relating to other interactions which are given by QK, which are charges of the compound, as well as two factors which scale inversely proportional with the absolute value distance to the electronic and atomic coordinates. So again, we can see that little r and big R are coming into play here in other terms in the Hamiltonian, which is demonstrating different scales and different positions of the compound in the space in which the interactions occur, in which we can probe and be able to experimentally measure, as well as more theoretically predict different properties of the chemical structure. And the change in energy, which is related to the change in the Gibbs free energy, appears in many molecular dynamics simulations, and a similar type of quantity appears in the alchemical Hamiltonian from the fact that there's a delta E factor, which is given as a function of the parameter of the atomic coordinates, which we had distinguished from the electronic coordinates in previous terms of the Hamiltonian that the authors described, which is defined as a difference in terms of two energies, which is very much relating to the change in the Gibbs energy, which is related to thermodynamic activity, which is going on in different compounds when a binding event or an experiment in an assay is being conducted, because it's looking at what is a change in the perturbation of the energy, which is reflecting what types of interactions are going on in the chemical structure, and how these individual terms, which either scale inversely proportional with respect to the electronic or with respect to the atomic coordinates, can determine and mediate which type of compounds would be optimal for either constructing different materials or demonstrating which molecular interactions are optimal for a given material application. And from the Hamiltonian, we defined the basis of the Hamiltonian to be annihilation and creation operators, which is also related to a very closely related electronic structure Hamiltonian, which I'll provide and draw the attention of the viewer to later in the presentation, just at the end, to demonstrate how there are many similarities between computational chemistry, electronic structure studies, and statistical mechanics and thermodynamics. And this is given by the fact that the commutation or the annihilation and the creation operators satisfy a commutation relation, in which, given by relation 8, the annihilation operators taking the Lie bracket of these two operators identically vanishes, as well as the fact that taking the Lie bracket of the creation operators also identically vanishes. And finally, taking the Lie bracket of an annihilation operator with a creation operator gives another term, which is proportional to a delta function, where these indices gamma and delta are specifying different regions of the molecular frame that we're studying the thermodynamic interactions of. In such a definition of the interactions of the Hamiltonian, like we had just mentioned, along with the change in free energy, or the change in energy and the change in the Gibbs energy or free energy in the alchemical setting, draw similarities to the electronic structure Hamiltonians and other related quantities. So this is related to a couple of videos that I'm going to be pushing on my channel at the same time, in which I'm drawing many different connections and applications between fast quantum algorithms, variational quantum algorithms, in silico molecular docking experiments and related studies, in which we think about quantum algorithms for electronic structure calculations and being able to apply these types of frameworks and methodologies from classical and quantum algorithms to study how, for example, the COVID-19 receptor and other disease receptors from a repository that I've looked at that's maintained by scientists in the Chinese Academy of Sciences can help us determine which type of algorithms perform better for different types of compounds, and if there exists any type of rotational symmetry in a compound, whether we could make use of that and take advantage of that in the encoding of the qubits that we're using for time evolution in our quantum circuit. And this is to say that we can define many related quantities to study the electronic structure, because as we see in the second line of the slide, we can describe or define an electronic structure Hamiltonian, which is given by annihilation and creation operators, either a two-point interaction between annihilation and creation operators, as well as a four-point interaction between annihilation and creation operators. And this is all relating fundamentally to probability, because in quantum mechanics, we can't measure with infinite precision at the same time the position and momentum of a particle in space. And so this is very much posing constraints about the type of resolution and ensemble behavior that we would expect to be able to extract from different molecules and compounds and materials on a larger macroscopic scale beyond individual atoms. And then from the electronic structure Hamiltonian, we can also define one-point electron and two-point electron correlators, which are given by two expectation values, which differ from the fact that in the 1-point electron correlator expectation. We have I and J terms appearing in the Braun-Ketz state in the expectation value, whereas in the 2-point expectation value for the electron correlator, we have I and J instead of just I, and K and L instead of just J, which both amount to two integrals with respect to either the spatial variables dr1 or dr1 and dr2, which we can evaluate for being able to quantify and qualitatively compare structures of different compounds. And there are similarities between, as we've been mentioning, between statistical mechanics in these areas from some of my own papers that I've looked at, which can be viewed on the archive or other presentations in this channel, in which I've looked at the Hamiltonian of a spin chain and made connections with the 6-vertex model, which is related to a square ice or three-dimensional ice model in case of the three-dimensional 6-vertex model, which is helping us get many connections with quantum chemistry and the original research of interest that was mentioned by Linus Pauling. So we can see that in the definition for the spin chain Hamiltonian from another reference, they define in terms of different interaction terms, 3 interactions, which appear in terms of the Hamiltonian, which is given by nearest neighbor interactions, as well as a derivative of K matrices, which are used in the definition of the transfer matrix to encode boundary conditions imposed at one end of the spin chain, as well as for a final term in the Hamiltonian, a trace of a product of K matrices with the Hamiltonian, which is normalized, and the trace of the K matrix for boundary conditions at the other end of the chain. So this is just very much to say that there are other expressions for other families of Hamiltonians, which can help us think about whether there could be any other Hamiltonians of interest that one could either characterize more from a rigorous pure mathematical perspective, also more of an applied perspective, which are relating to thermodynamic interactions appearing across many different fields at the same time. And as we had just mentioned, the spin chain Hamiltonians share in many connections with thermodynamic interactions predicted by seminal work of Pauling in introducing the 6-vertex model, which is given by an ice model, or a vertex model, which is given by the constraint that about every vertex of the square lattice, we have the constraint that the number of arrows pointing inwards and outwards of each configuration is even or is 2. And you can look at different types of generalizations or even degeneracies in which the sample space of the 6-vertex model can either become larger or smaller, depending upon whether you can allow either 0 arrows to point in at every vertex or 4 arrows to point in or out of every vertex, which can either enlarge the sample space to the 8-vertex model or make the sample space a little bit smaller to the 5-vertex model. And besides the arrow representation, which is related to the height function of the 6-vertex model, there are also line representations, which can represent configurations from another version of configurations from the arrow orientations of the 6-vertex model, which all lend themselves to many thermodynamic interpretations that I've looked at and discussed in previous videos on the channel. And so the outcomes that we want to describe is that we describe the all-chemical Hamiltonian structure with the potential of such a Hamiltonian to numerically model different properties of materials with quantum algorithms. And we establish how electron-electron and nuclear-nuclear interactions appear through potential terms in the definition of the all-chemical Hamiltonian. But even though we were describing more of the supply perspective at the beginning, we can still make either connections with statistical physics in more rigorously classifying these finite volume systems for compounds and molecules and materials, as well as an algorithmic perspective through quantum algorithms and being able to benchmark classical and quantum computing methods for determining whether a quantum algorithm can still live up to the hype, so to speak, and demonstrate some type of speed up while still being able to deliver a high fidelity approximation for different structures of the, or different qualities of the structure, materials, and compounds. And to this end, pursuing new directions of research relating to the design of Hamiltonians for simulating intriguing properties of novel materials continues to remain of interest. And so to conclude, between applied and pure mathematical perspectives, unknown properties of materials can help elucidate new perspectives on classical arguments of statistical mechanics and also help us think about more applied perspectives at the same time. And thanks for watching.